Okay, stop and think about this for a second. The exact same fundamental laws of physics that are creating the light from your screen are also the reason your eyes can even process that light. It's all connected. So for the next few minutes, we're going to connect those dots, all the way from the power plant right to your pupil.
So let's really break it down. First question, how in the world do we make the electricity that's powering this screen you're looking at right now? And second, how does physics step in to help our eyes make sense of all the light it's creating? It's a journey from the absolutely massive to the microscopic. Let's kick things off with power.
First up, power. You know, the electricity we depend on every single second of every day? It doesn't just appear out of thin air. It has to be generated. So how does that happen? Well, the answer lies inside a pretty remarkable piece of engineering. And that piece of engineering is the electric generator. Just think of it like a translator. It takes mechanical energy, like the spinning of a turbine from wind or water, and it converts it into electrical energy. The real magic here is a principle called electromagnetic induction. And it basically says that if you move a magnet near a wire, you create an electric current. It's that simple idea, just scaled way, way up, that powers our entire world.
But, not all electricity is created equal. There are two main types, AC and DC. AC, or alternating current, is what's zipping out of your wall socket right now. Its biggest advantage? It's super easy to send over long distances using transformers. That's why it's perfect for our homes. Then there's DC, direct current. It only flows in one direction. It's not so great for the power grid, but it's an absolute beast for things that need huge, steady power, like the giant motors that run a subway system. So, we've got our power. It's generated and ready to go. But using that power comes with a side effect. It's an unavoidable physical reality that affects every single wire, every electronic device out there. And that side effect is heat. Yep, anytime an electric current flows through a wire, whether it's in a tiny microchip or a massive power line, some of that electrical energy gets lost as heat. It's just the price we pay for power. And this isn't random, it's all laid out perfectly by Joule's law of heating. Now, the most important part of this law, the part you really need to get, is the relationship between current and heat. It's not one-to-one. Get this. If you double the electric current going through a wire, you don't just get double the heat, you get 4 times the heat. That little squared in the formula is a huge deal, and it's why engineers are so obsessed with managing current in everything from your phone to the power grid.
But here's what's so cool about this. On one hand, it's a problem, right? Engineers are always fighting to reduce that heat loss. But on the other hand, we totally use it on purpose all the time. Your toaster, your electric kettle, even an old school light bulb, they're all designed specifically to use Joule's law. They cram current through a material with high resistance to deliberately generate a ton of heat. Even an electric fuse is just a clever trick. If too much current flows, it gets hot enough to melt itself, breaking the circuit and saving your more expensive stuff. Pretty smart, huh?
Okay, so we've covered the physics that powers our world. Now, let's totally switch gears and look at the physics of how we see it. Because believe it or not, the same science that explains power lines also explains the most amazing optical instrument we have, our own eyes. A whole lot of us have vision issues like myopia, which is just nearsightedness, or hypermetropia, which is farsightedness. If you're myopic, distant stuff is blurry. If you're hypermetropic, it's the close-up things that are a problem. Well, physics has the fix. For myopia, you need a concave lens, which spreads the light out, and it always has a negative power. For hypermetropia, you need a convex lens to bring the light together, and it has a positive power.
Now take a look at this number, negative 1.25 diopters. On its own, it's just data. It's the answer to a math problem.
But it is so much more than that. For someone whose vision gets blurry past, say, 80 centimeters, this simple number, this result of plugging things into the lens formula, is completely life-changing. It's the exact prescription needed to take their limited, fuzzy view and bring the entire world into sharp, clear focus. It's a perfect example of the incredible power of physics.
Okay, so let's take that idea of clear vision and push it way further. What if we want to see things that are not just far away, but also incredibly close together? I'm talking about 2 distant stars that, to us, just look like a single bright dot.
This is where a concept called resolving power comes in. And here's the key idea. This isn't about making things bigger. Magnification is easy. This is about making things distinct. A great telescope's real test is whether it can look at what your eye sees as one star and reveal that it's actually 2 separate stars shining right next to each other.
So how do we know if we can tell them apart? Well, a scientist named Lord Rayleigh gave us the perfect test. Check out this diagram. On the left, those 2 points of light are clearly resolved. You can see 2 separate peaks. On the right, they're a total blur, just one big blob. But that picture in the middle, that's the sweet spot. That's what we call just resolved. It's where the main peak of one light source falls perfectly into the first dip of the other. Any closer than that, and they mush back into one.
So, what's the big takeaway here? The crucial point is this. To see finer and finer details, you don't need a longer telescope, you need a wider one. A larger diameter lens or mirror directly boosts its resolving power. This is the whole reason we build absolutely gigantic telescopes like the James Webb. Its huge mirror isn't just for sucking in more light, it's to get the incredible resolution we need to tell one distant galaxy from another.
Wow. So we've gone from electric generators all the way to the lenses in giant space telescopes. But none of this knowledge just appeared out of nowhere. It was all built carefully, piece by piece, by following a structured way of thinking, a kind of blueprint for making sense of the universe.
And this structured approach is something we all learn, right? It's formalized in science education all over the world. The whole point isn't just to make you memorize a bunch of facts. It's to give you a framework, a blueprint that guides you from the simple ideas to the really complex stuff, making sure our understanding is built on a solid, logical foundation.
And the goal of that framework? It's not just about knowing formulas. I mean, look at this quote right from the curriculum's aims. It's about developing your thinking process, your imagination, your ability to solve problems. Physics isn't just a class you take, it's a toolkit for your brain.
So from creating the power that runs our entire civilization to crafting the lenses that let us see to the edge of the universe, physics gives us the fundamental tools to both understand and shape our reality. The only question left is, with these amazing tools in our hands, what will we choose to discover next?